This is Higher Physics Notes, Unit 2, Section 7, Emission and Absorption Spectra, the final part of this, Part 3 on line spectra. If you're writing your notes up just now, what you should do is pause the video at this diagram and then copy up the diagram before proceeding, because I'm about just to say a few things about it. Well, you can see in the top row of the diagram we have a white light source, in this case a lamp. It's emitting light which passes through a prism and is observed by the observer. And of course, all colours of the visible spectrum are emitted: red, orange, yellow, green, blue, indigo and violet, and all the colours in between. And what you see then is a continuous spectrum. It says continuum there, but we normally call it a continuous spectrum. Continuous because there are no gaps in it. All frequencies, that is, all wavelengths of visible light, are present. If we then, in the middle row, take a gas and we heat that gas, the heat energy that we give to the gas causes electron promotion to an excited state. The electrons, when they get into the excited state, are unstable, so they fall back down, and they fall back down between two specific energy levels and therefore give off a photon with a specific energy, i.e. a specific wavelength and specific frequency, therefore specific colour. So depending on the particular downward transitions in the particular gas atoms we're dealing with, we get particular colours emitted. And that produces the line emission spectrum, which you can see. You only see specific colours of line because we only get specific downward transitions in particular gases. And each gas has its own particular set of downward transitions that happen, and therefore each gas has its own specific line emission spectrum. And it acts a bit like a unique barcode for each gas. So neon has a specific line emission spectrum, oxygen has its own unique one, hydrogen, and so on and so forth. So that's the line emission spectrum. It's basically black with these coloured emission lines superimposed on the top. What's interesting though is if you take the same gas that has just produced these emission lines, and incidentally you can also produce them not by heating the gas but by putting a very high voltage of several thousand volts across the gas and forcing it to conduct. The electrons that pass through carry a lot of electrical energy because of the high voltage, and they energize the electrons up and cause promotion and emission as well. So that's an alternative. Anyway, if you take that same gas and you allow it to be cold, by cold we mean room temperature, and then you pass white light through it, and then pass that resulting light through a prism again, you find that you get all the white light continuous spectrum effect again, but there are black lines in it. Certain colours have been removed, and this happens because the gas, when cold, will absorb particular frequencies of photon, that's particular colours of photon, at exactly the same frequencies or wavelengths that it previously emitted at when it was hot. So you can see that the line emission spectrum and the line absorption spectrum are like negatives of each other. If you were to imagine sliding that emission spectrum downwards, it would fill in the gaps in the absorption spectrum. So just to make the link between the energy levels and the colours, you'll remember that if an electron falls, let's just say between E2 and E1, so it's been promoted up here because of the heating of the gas. It's unstable up there, so it spontaneously falls down. When it falls, the energy is emitted as a photon, energy E is hf. Now remember, V is F lambda, as you know. So for electromagnetic radiation, that becomes C is F lambda. So we could say that F equals C over lambda. Why am I doing that? Well, the photon energy is HF. This is for a photon. We could replace F with C over lambda. So we end up with a situation where that's Planck's constant, that doesn't change. Speed of light doesn't change. So if you've got a big downward transition between E2 and E1, you've got quite a big energy in the photon. And a big energy means a small wavelength. That's nearer the violet end. So the energy of the transition determines the wavelength and therefore the colour of the light. So the reason you get these different coloured emission lines then is because of different downward transitional energies. This was an interesting observation, this whole idea of absorption spectra existing, because when astronomers first looked at the sun, they saw absorption lines, and they matched them with the absorption lines of the gases that they had experimented with on Earth, and discovered that the absorption lines were the absorption lines of hydrogen. So they were seeing absorption lines in the otherwise continuous spectrum of the sun. And here was what was happening. You can see on the left there is the sun. The sun has a hot interior, but a slightly cooler atmosphere. And, well, distinctly cooler atmosphere, actually. So all colours are generated in the hot interior, along with non-visible wavelengths as well, actually. So you've got this whole full continuous spectrum coming out from the core of the sun, where it's very hot. It passes through the cooler atmosphere, so you've got to think of the cooler atmosphere as being the cool gas. And if you look at the energy level diagram there, the Bohr atom, what happens there is that electrons are excited and are promoted up to higher energy levels. These are transitions. And they therefore remove photons from the visible spectrum at specific energies which match the energy gaps. They're moving up through the energy differences. Therefore, you get a continuous spectrum with the dark absorption lines, and that's what the astronomer there on Earth is seeing when he observes this. So that was the first evidence that we had, actually, of the fact that there was hydrogen in the outer atmosphere of the sun, and that gave us proof, because we matched the absorption lines we observed from the sun with known absorption lines for hydrogen on Earth. There we are. And that brings us to the end of 2.7 emission and absorption.